Hello everyone, welcome back to another video for the series. I'm Q and uh, today I brought a very fun and interesting problem from this year's 2025 IMO. Problem number one, and the reason why I love this problem is because it took me 20 minutes to solve and write out my solution. But the funny thing is, it took me like 10 minutes to understand and 7 minutes to solve it, and the other 3 minutes to write my solution. So I think this problem is interesting because it actually took me more time to understand than solving. So that's why I love this problem. And I later compared my solution with the official solution, but they were really similar to each other. So today I'll just share my personal solution because I think that way I can share my thought process. And yes, so without further ado, let's start. A line in the plane is called sunny if it is not parallel to any of x-axis, y-axis, and the line y equals negative x. So like these lines are sorry, this is sunny, this is sunny, uh, uh, this is sunny. Let n greater than or equal to 3 be a given integer. Determine all non-negative integers k such that there exist n distinct lines in the plane satisfying both of the following. Yes, this sentence is quite tricky, uh, but I think we could reword it. So I think instead of trying to determine all k, non-negative integers k, we could think of it like this, I think. We can count the case when k, we can examine the case when k equals 1, k equals 2, 3, and so on, and choose k's that work from there and count them. Or we could count when n equals 1, n equals 2, and so on, and then we can find out k from here and here and here, and then count our k's from here. So those are two approaches that we can take. So determine all non-negative integers k such that there exist n distinct lines in the plane satisfying both of the following. Now, by looking at these two cases, these two criterias, I think we can determine which approach to use, counting for k or counting for n and then k. For all positive integers a and b with a plus b less than or equal to n plus 1, the point a comma b is on at least one of the lines. And one of the line means one of the n lines. This doesn't really help because we don't have k here. Now the second one tells that exactly k of the n lines are sunny. Exactly k of the n lines are sunny. So I personally think taking this approach is better because, like, let's say, oh, wait, it's 3 and 4. Because when we examine the case when n equals 3, we could also find a comma b that satisfies the first one, and then we can also determine k that works in this situation. So because this k depends on n, I think it's better to use our second approach. Then let's try with our second approach. And obviously, the first one would be when n equals 3. Now, because there's no upper bound, I was pretty sure we can find a pattern, or we could use like induction, because the problem would not ask us to find infinitely many study infinitely many cases of n. So to find a pattern, let's start with n equals 3. For all positive integers a and b with a plus b, the point a comma b is on at least one of the lines. So what I did at first is I just graphed them because, like, why not? this case, a plus b is less than or equal to 4. So, and a and b are positive numbers, so 1, 1, 1, 2, 2, 1, 3, 1 works, 1, 2, and 1, 3 works, and 2, 2 works. So these are all a, b, and they are on at least one of the n lines. So one of the 3 lines. And exactly k of them are sunny. So let's see. This one, and this one works. And how many of them are sunny in this case? 0. So in this case we get k equals 0. So now it might be confusing at first because it says determine all non-negative integers k such that there exists n distinct lines. But we're supposed to find n that's from k. But this case we found k from n. But it's totally fine. This approach is totally fine because this case, when n equals 3, is just a subcase of when k equals 0. So we already know this works. So k equals 0, it works because there exists a case when n equals 3, and this works. If it shows k equals 1, then we could also say that if this case, if it leads to k equals 1, then we can say k equals 1 also works because there exists a case when n equals 3, and you have some kind of diagram here. So we're thinking in opposite way, but it's totally fine because we are counting the subcase, so we are studying the subcase right now, but we already know that the subcase is within the case that we want here. So studying this will help us find this because there exists multiple big ones. So these are k's and these are n's, something like that. So if you find an n that works, then we know this k works because there exists a subcase here. But if it doesn't have subcase, then this doesn't work. So studying n would be sufficient. Let's see if we can get another case. This one, we could also have this one, 1, 2, 3. Or I will say this one like this. So that, or something like this. So that we get k equals 1. The other one would be, can we get k equals 2? Let's see if we can get k equals 2. 1, 2, no. Let's see. If we can get k equals 2. So 1, 2, 3. Oh, we got k equals 3. But can we get k equals 2? So if we get one like big one like this, or something like this, or like this, we cannot get k equals 2 because this will lead to k equals 1, this will also lead to k equals 1, and this also leads to k equals 1. So this doesn't work, and this one, we can also, it mirrors, so it's the same. We don't have to think about this one and this one because we already counted for this. Then we should take a different approach, maybe like this. We get 1, k equals 0. This one doesn't work, this one doesn't work, so it doesn't work. Yeah, then it tells us that there is no way that we can get k equals 2 because we just counted every case. Because we counted case for this one, this one, this one, and this one, And turns out there are no case that gives k equals 2. So these are all the case that we can get from case n equals 3. Now let's take a look at when n equals 4. We get 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, like this. Now notice that if you have this, or if you have this, or if you have this, it's the same thing as n equals 3. So we should not include a big line like this. That's great. Then notice that we anyways have to have 4 lines that passes through the 4 points, this one, this one, this one, that one. But we cannot have something like this. Meaning, each 4 lines should pass this individually, not like this. So it could be something like this, but it doesn't work because we have this one. So yeah. So let's connect them, because we cannot connect anything from here to here and here to here. The only cases are this one, or this one, or this one. But if you have them like this, then this one, it also gives us this, let's say, this, we have 2 dots left over. So this case doesn't work. And yeah, and it kind of tells us that it is impossible for us to have n equals 4 without a big line like this. Because 4 lines must pass through 4 distinct lines passes through each of the points here. So each of the 4 distinct lines passes through each point in here. But let's say we have done that. How many dots do we have here? We have m plus 1 times n over 2. This is the total number of dots that we have. But we have 4 lines that passes through, let's say we have n lines without loss of generality. No, not without loss of generality. To generalize it, let's say we have n lines, and there are this much points. Then on average, a line must pass through this much of the points, or dots. But it is impossible without having a big or long lines, because we will have a dot left over. And we can prove that by doing this. So this is when n equals n. We have n dots, and from here, like this. These are all the dots that we have, and also there are dots within here. Okay, let's say there is a line that because we have n lines, and each line must pass through 3 points from here, here, and here. So each line from n must pass through only exactly, so each line from n lines must pass through exactly 1 point from here, here, and here. But notice that that's impossible because say if this passes through, if a line passes through this one it does not pass through a dot from here, meaning we will have a dot left over. Here and here, we might get a point, luckily, that connects all the 3 points here, but no, actually that's not possible because anyways it will form a triangle like this, and triangles can never become a line, so it's impossible for there to exist a case without having one of these big lines. So we just proved that every case must have one of these long lines. But if you have one line that's this long, then it's the same case as counting n minus 1, the case for n minus 1. But the case for n minus 1 also must have a big line like this, so it's actually the same case as n minus 2. And it's all the same until we get 3, because we cannot have n smaller than 3. But when n equals 3, we found out that k equals 0, 1, and 3 works. K equals 2 doesn't work because we tried every case. So we just proved that every case leads to n equals 3, because every case must have a long line, this 3, at least one from these 3. So every cases are equal to when n equals 3, and when n equals 3 we have k equals 0, 1, 3. So when k equals 0 we might have multiple n's, when k equals 1 we might have multiple n's, k equals 3 we might have multiple n's, but there are no n's that gives other k's. So we could safely say that k equals 0, 1, 3 are the only possible values, and that completes our proof. Yeah, so as you might have noticed, the solution itself is not that difficult, but understanding and trying to like unsolve it. So you have to count k. We have to count k that has n, but we counted n that has k. So I think this first logic was difficult in this problem, and I really love solving this because, as you know, if you've been watching the videos, I kind of gave up on like combinatorics, but I think this is a combinatoric problem, but yes, it was better than other algebra and geometry in the year 2025. So I really love solving this problem, and if you also enjoyed it, please don't forget to like and subscribe. And thank you, and I'll come back with another very fun and interesting problem. Thank you, and see you tomorrow. Bye.